This lesson supplements the previous two on FMS by adding some points in order to tailor the course specifically for the radio navigation syllabus and examination. They cover Kalman filtering, data entry, reversionary modes, and radio updating. Let's start with Kalman filtering. You will remember from your flight instruments lessons that inertial navigation systems and their successors, inertial reference systems, are subject to both Schuler or bounded errors and ramp or unbounded errors. Their effect over time is a combined error growth pattern, which looks like this. Unlike our earlier diagrams, which were idealized, this is an actual plot of INS against GPS on a test flight. The pattern can be clearly seen. There is a basic ramp increasing at approximately 1 nautical mile per hour, with a 1 mile Schuler oscillation superimposed on it. How can we correct or remove these errors? The answer is that we can't. All of these bounded and unbounded errors result from limitations in the accuracy of the components of the INS. They arise from the accelerometers, the integrators, and the gyros. They can all be considered to be a more sophisticated form of instrument error. There is nothing that can be done about them within the INS itself, except to improve engineering standards. And this did happen with the evolution of better and better manufacturing techniques during the 70s and 80s. Even with these errors, the general accuracy of an INS is good compared with previous systems. This plot shows only an 8-mile error after 9 hours of flight. For a standalone system, this is very good. However, from the 90s onwards, two developments occurred. One was the introduction of the ring laser gyro to replace the old tune rotor gyros. Systems using these new gyros were usually called inertial reference systems. The other was the idea of using the INS or IRS as only one component of a multi-sensor system, and to have a method of extracting the most probable position from a combination of all of the inputs. This multi-sensor system is part of the Flight Management System, or FMS for short. And the method of establishing the most probable position from a variety of inputs is called Kalman filtering. The later generation of inertial systems, which are generally known as inertial reference systems, or IRS, are usually part of an integrated flight management system, FMS. In the flight management computer, or FMC, there are usually 2 or 3 IRSs, each generating its own present position. These IRS positions are compared with independent sources, such as Global Positioning System or GPS, and computer-generated calculation of crosscut positions, which have been obtained from ground-based radio beacons called distance measuring equipment. The computer automatically selects those DME stations along the route which will give the best crosscut, and calculates an independent new position several times a minute. The crosscut positions are called DME positions. Not all inputs are always available. DME is a line of sight system, so it can be blocked by hills or the curvature of the Earth. GPS can have blank spots. A process known as Kalman filtering produces a statistically most probable position, known as the FMC position. From this FMC statistical best estimator position, it is possible for the FMC to establish an error trend over a period of time, and to build mathematical models of both the Schuler and the unbounded error propagation pattern. This is then used in the computation of future computer-generated positions. Kalman filtering is complicated and does not lend itself to broad simplifications. However, it is important to realize that the FMC position is not the average of the IRS and DME or GPS position, but is computer-generated using a sophisticated statistical algorithm. We'll move on to data entry now. When keying navigational data into the control and display unit, the valid formats are latitude and longitude as either a 7-figure group alphanumeric if entering to the nearest degree, or as a 15-figure group if entering to the nearest 0.1 of a minute, which is more usual. Up to 5 alphanumerics are used for ICAO aerodrome designators, reporting points, navigation facilities, airways designators, and runway designators. Up to 7 alphanumerics may be used to designate SIDs and stars. We have already covered the primary mode and 2 of the reversionary modes, which, if you recall, were dual mode, independent mode, and single mode. There is also a backup mode, in which both FMCs fail. In this case, the IRS information is used directly in the EFIS. A limited flight plan is held in the CDU. No FMS autopilot couple is available. Let's look at high-latitude data flow now. The normal data feed from the inertial reference systems to a dual FMC system is as depicted here. When operating at latitudes above of 84 degrees north or south, the FMC will decouple the IRS, with the left FMC using the IRSs in the order left, centre, right, and the right FMC in the order right, centre, left. The reason for the decoupling is to avoid large longitude errors being created by high secant values at these high latitudes. Finally, we'll look at radio navigation updating in the Kalman filter. The IRS positions can be filtered against GPS, DME-DME, VOR-DME, or localizer, with the preferred priority depending on the radio navigation aids fitted to the aircraft and the software vintage of the FMS. However, the EASA ATPL radio navigation exam uses one of the designs fitted to the Boeing 737-400 for some of its specific questions. On that model, there was no GPS at the time, and the VOR-DME option was discarded as being too inaccurate. Therefore, for the Boeing 737-400 only, the only source of radio navigation updating is the DME-DME option. This concludes this lesson, and with it, our study of flight management systems.